Bismillahirrahmanirrahim. Absolute potential energy. In the gravitational field, absolute potential energy of a body at a point is defined as the amount of work done in moving it from that point near the surface of Earth. That point can be first point, second point, third point, fourth point, any point near the surface of Earth, to a point where the gravitational field is zero or force of gravity becomes zero. We repeat it. In gravitational field, absolute potential energy of a body at a point, either it can be first point or second point or any other point, absolute potential energy at any point is defined as the amount of work done in moving that body from that point, which is near the surface of Earth, to a point where the gravity becomes zero. So it means this is the amount of energy which is stored in moving any body from a certain point to a point where the gravity becomes zero. And this amount of energy which is stored is known as absolute potential energy at that point, either at first point or at second point or third point. At any point, the absolute potential energy is the energy which is equal to the amount of energy stored in that body in moving it from that point to infinite point. Mathematically, we can determine that absolute potential energy by the following procedure. Consider a body of mass m which is lifted from point 1 to point n in the gravitational field. The distance between the 1 to n is so large that the value of g is not constant between the 2 points. As we know that point n is at such a distance that the gravity becomes zero, and it is a huge distance. So we divide the distance between the first and nth point into large number of small distances. As to calculate the work done against the force of gravity, the simple formula W is equal to F dot D cannot be applied, as the force between first to end point, force of gravity, because of the earth or attraction of the earth, which is a force, is not constant throughout the distance between first to end point. So, to calculate the work done from 1 to end point, we divide the entire displacement into large number of small displacements of length equal to delta r. The interval delta r is taken so small that the value of g remains constant during this interval. Now we calculate the work done in moving the body from point 1 to 2. For this work, the value of constant force F may be taken as the average of the forces acting at the ends of the interval delta r. To calculate the work done from first point to second point, we take the average force between first point and second point, and that average force is taken for more precise calculation, as we know that at point number 1 the force of gravity will be more, and at point 2 the attraction of the earth will be less, or the force of gravity will be low. So we have taken the average force between first point and second point. To take the average, we have not used the value of distance r1 or r2 for calculation of force or force of gravity. Instead, we have taken the average of R1 and R2, which is almost equal to R. And this R square is taken as equal to R1 into R2. So this is the value of R, which is the geometric mean of R1 and R2. If we take the under root of R1 and R2, both sides of this equation, then R will be the geometric mean. And R is the mean distance from the center of this interval to the center of Earth. So average force is being used for calculation of work done over here in this case. So to calculate the work done from first to second point, we use the scalar product of force and the displacement delta R, F dot delta R into cos of 180 degrees, as we are moving upward or displacing upward, and the force of attraction is in downward direction, so it will be a negative work, and the angle will be cos of 180 degrees. Angle will be 180 degrees, and cos of 180 is equal to -1. So net work done in moving the body from first to second point is equal to minus F dot delta R. And what is the value of F? That is G capital M small m over R square, where capital G is the gravitational constant, capital M is the mass of the earth, small m is the mass of the body which is being moved from first point to nth point. Over here in this case from first point to second point, and delta R is the distance between first and second point. As we know that delta R is equal to R2 minus R1. So the work done between first to second point is equal to G M small m, and this bracket is come from the simplification of these two terms. When we divide R2 by R1, R2, 1 over R1 will be the result, and similarly minus 1 over R2 will be the result after division by R1 into R2. So work done from first to second point is equal to minus G capital M small m into 1 over R1 minus 1 over R2. You see that over here G is a constant term, capital M is a constant term, and small m is a constant term, as these doesn't change during the motion from first to second point. Similarly, if we move from second to third point, these terms will remain same. Mass of earth remains same, mass of the body remains same, and universal constant, gravitational constant remains same. Only the distances changes when we move from second point to third point. So we change the distances 1 over R2 minus 1 over R3, and similarly we move further, and when we reaches between the n minus 1 point to n point, the formula will reshape into this situation. The formula will be reformed as minus G capital M small m bracket 1 over R n minus 1 minus 1 over Rn. Now we have calculated all the work done between all intervals from first to n intervals or n points. So total work done is equal to work done from first to 2 plus work done from second to third, from third to 4, and up to so on from n minus 1 to n. Putting the values of all the works in this equation, the final shape is this, and if we simplify, then R1 1 over R2 will be cancelled by 1 over R2, and minus 1 over R3 will be cancelled by minus 1 over R3, and so on. Minus 1 over Rn minus 1 will be cancelled by plus 1 over Rn minus 1. And only the first and the last term will remain not cancelled. All the remaining terms will be cancelled by each other. So the total work done is dependent only upon the first distance Distance of the first point from the center of Earth to the distance of the end point from the center of Earth. And we know that distance from the end point to the center of Earth is very large or almost infinite distance. So 1 over Rn will be a very small value. When the denominator is very large, the net result is almost very small. So we neglect 1 over Rn minus 1, 1 over Rn, and the remaining term will be 1 over R1, which can be written as total work done is equal to G capital M small m over R1. You see that in moving from first point to end point, the distance, the work done is dependent upon the distance from the center of Earth of the first point. If we want to calculate the absolute potential at the second point, then R1 will be changed to R2. If we want to calculate the absolute potential at any point, we will place the distance of that point from the center of Earth over here, and the result will be known as absolute potential energy or absolute gravitational potential energy. As we have already defined that absolute potential energy of a body at any point is defined as the amount of work done in moving it from that point to the point where the gravitational field becomes zero. So we have calculated the formula, or we have derived the formula, which is known as absolute gravitational potential energy. Thank you, students, for watching the video. Please continue watching our lecture series and subscribe our channel. For more information, please visit www.kencollege.com.